zero knowledge. Thank you very much. Good morning, everyone. My name is Hussein Hamadi. I came here on behalf of Dr. Huda Al-Khazami. Okay, she had to catch another conference in Europe, so I would like to send her regards to all of you. And I will be your session chair for the next, I think, 1 hour and a half or something like that, till 12. So allow me, first of all, to introduce the topic of this session is actually zero knowledge and MPS, which is actually multi-party computational. We will talk about, we will give the first session topic, which is efficient NIZK arguments, and straight line simulation and extraction. Will be presented by Michel Champy. I hope I'm calling the name right. Yeah? Okay, very good. So I will allow Dr. Michel to introduce himself. Okay. Ivan?
It's okay, don't worry.
I'm very sorry, okay? It's a very short notice. Thank you.
No problem, sure.
Thank you very much. Okay, so the stage is yours.
Thank you.
Thank you.
Thank you for the introduction. So this is a joint work with Michele Ciampi. I'm Ivan Visconti from University of Salerno. The title is Efficient Needs Arguments with Straight Line Simulation and Extraction. Okay. Good. I'll start with an introduction on what non-interactive zero knowledge is, since the audience of Kant is not homogeneous, so it's better to agree at least on the notation. So we are in a setting in which there is a player, a prover, that would like to send a proof that is just one message. Send the proof not to a verifier, but to a place where everyone can read and be happy with it, can verify it. So the proof pi in this example, it's a proof that a claim X is true. Okay, so everyone has X, and the prover, in addition to X, has a special information, an auxiliary information that is a witness. The point of being zero knowledge, such a proof, is that the proof is privacy preserving, in the sense that the auxiliary information of the prover, that is W, it's kind of protected, remains private. Examples. X can be a statement where the prover wants to prove that two ciphertexts C and C prime correspond to the same plaintext, for instance. Okay, so the verifier knows the statement, and the prover can prove it because it has a witness. A witness is, for instance, can be the pair of messages that are encrypted in the two ciphertexts and the randomnesses. And usually you can use it to prove any NP statement. So if the X is an instance of a language that belongs to NP, there is a witness to verify it, and therefore one can build a non-interactive zero-knowledge proof for it. That's another example. You can prove that RSA is destroyed if you have a proof that breaks the RSA assumption, and you can give a non-interactive zero-knowledge proof so that nobody will know why this is true, but you prove that this is true. Well, assuming this is true, I don't know if it's true. Okay, so why do we study non-interactive zero knowledge? First of all, it's interesting on its own because it's a natural theoretical question, and there are people that are happy just with this, and unfortunately, this is true. Then there are also applications. This is a building block to construct cryptographic protocols. Or primitives. Indeed, for instance, it's well known that Naor Jung showed how to get CCA security starting just from CPA security and using non-interactive zero-knowledge proofs. It's actually used in practice. The cryptocurrency Zcash that is around already since a few years, and it has a very significant market capitalization, uses non-interactive zero-knowledge proof in order to show that the transaction is correct, it's not a double spending, and preserving the privacy of the sender and receiver and the amount in the transaction. Okay, so it's an extremely important tool, both in theory and in practice. Okay, let's go a little bit more into the details of the definition, even though it will remain with a high-level formalism. So we want a few properties. One is completeness. Completeness means that the verifier will accept the proof if the prover computed it correctly using the witness. That's it. So soundness means that if actually the statement is false in the sense that X is not a truth statement, then it's extremely unlikely, so negligible probability, that the verifier will accept the proof for it. The zero-knowledge property means that basically this proof does not leak information about the witness, and it's formalized usually asking the existence of an efficient simulator that does not have a witness and still can produce the proof pi. Another property that is often used in the applications is the proof of knowledge property. This requires that not only the prover can compute the proof that is accepted by any verifier, but also there is basically the prover must know the witness showing that X is true. Okay? So the witness is in his pocket. This is important. It's an additional property. It's not implied by soundness. All right. So it's a beautiful object, but we know that non-interactive zero-knowledge is impossible to construct without introducing some potential points of failure. What does it mean? It means that there cannot be such a proof system. Otherwise, if there is, for instance, a simulator, here you can see if there is a simulator for the zero-knowledge property, a simulator that can compute such proof without a witness, then a prover, malicious, can use the same strategy of the simulator to compute a proof of a false statement. Okay? That's the basic intuition why this is impossible to achieve, unless the simulator exists because it has some special features that an adversarial prover does not have. In this case, the adversarial prover will not be able to run the simulator. Okay. But now I'm introducing these additional features. In some talks they call it setup to make it mild so that it looks good. From my point of view, you are then constructing a needs to protect, to get soundness, to get zero knowledge, but you are adding, in order to construct it, a potential point of failure. Okay. Okay, what are these potential points of failure? So the most used one is the common reference string. This is the setting that was proposed originally by Blum, Feldman, and Micali when they introduced non-interactive zero-knowledge proofs. And what is it? It's a trusted parameter. So basically, there is somebody that everyone trusts that generates some parameters, and these parameters now are available to everybody. And now, okay, in this setting, it is possible to have these beautiful proofs. But everyone must trust the parameter generator. Okay, so this is very nice. Of course, it is a point of failure because the parameter generator can, could, for instance, prove false theorems knowing some auxiliary information associated to the parameters, to the CRS. Okay, because of this, along the way, there have been ideas not to have just a trusted party generating it, but using multi-party computation, and so on. Okay, anyway, this is something that has been used. Even the cryptocurrency Zcash that is currently using non-interactive zero-knowledge proofs used the trusted parameters and also used the technique of generating them through a multi-party computation. Usually, in this setting, there is a limited efficiency. So, I mean, constructions are not that efficient as we would like to be. So there is another setting to obtain non-interactive zero-knowledge proofs, and is in the random oracle model. So basically, we assume there exists a random oracle. It's kind of also related to the previous assumption, because what is a random oracle? A random oracle is somebody that receives an input and answers with a random answer. Okay, random string as an output. If you ask another question, another query, there will be another random answer. If you ask the same question twice, you get the same answer twice. Okay? So this can be a third party, again, like before. But actually, the situation is slightly better. We don't really need the third party because there is something that looks like, say, as safe as a trusted party, which is a cryptographic hash function. So like you might use SHA-256. instead of the random oracle to implement the random oracle. And then basically everyone, without involving third parties, can enjoy this beautiful tool. Okay, this has been used for a long time, and there are basically efficient protocols that using an hash function, it is the Fiat-Shamir transform, produce a non-interactive zero-knowledge proof. But there are some caveats. Okay, let me see. Right, so what are the caveats? The caveats is that, for instance, in order to be sure that this is zero knowledge, that there is no leakage of private information, the simulator in this approach, with this approach, must program the random oracle. What does it mean? It means that basically the players, the malicious, the adversaries, that can be the verifiers in case of zero knowledge, they just have no idea about SHA-256, right? They have no idea. They cannot run it locally. They will just ask a query, getting an answer without doubting about the answer. And therefore, the simulator can answer whatever it wants. So that's why it's programming in the sense that it's deciding what are the answers of the oracle, okay? Okay, and also the proof of knowledge property has the same kind of problem in the sense that the extractor will have to also program the random oracle, maybe, or maybe we'll have to rewind. To rewind the prover means that we'll answer in some way, the prover will compute the proof, then the extractor will go back, will rewind the prover, answering a different, giving a different answer to the same query, and the prover will again compute the proof, and with all this material, the extractor can get the witness. Okay, so there are a few problems. So I was saying, you know, in any time, in any way you try to realize these systems, you introduce some points of failures. So, for instance, about the random oracle, it is known that the random oracle, the use of a programmable random oracle like here, it's dangerous when you want global security in the sense that there are multiple protocols and you are supposed to use the same random oracle, so SHA-256 everywhere. It is problematic because this idea of programming the random oracle fails, could fail at least. Why? Because the simulator will answer in one session to a query because it needs to complete the session in a secure way. But then there is another session where the same query might arrive, but the simulator in another session, in another protocol, might need to answer differently in order to complete the session. So it will not be consistent, and therefore this will be distinguishable from the natural behavior of a cryptographic hash function where the same input produces twice the same output, if you ask it twice. Okay, so ideally, if you want things to work out with programmable random oracle, you should use a different instantiation of the random oracle for every protocol execution, which is completely impractical. Okay, so it is kind of problematic when you want this type of security. Also, rewinding affects protocol composability, so it's very difficult, if not impossible, to prove that the system is secure if your security relies, for instance, on rewinding a player, like I mentioned for the proof of knowledge property. The same also under concurrent composition, there are issues if you make some specific non-black box use of the code of the adversary. This is a technique used to extract right away a witness from a prover computing information. They are called knowledge assumptions. They are also problematic. So basically, in the real world, we would like to instantiate the random oracle because it's efficient, because it allows to compute the needs, but using the same cryptographic hash functions everywhere and without having these problems that I mentioned so far. So that basically come from rewinding, come from non-black box use of the code of the adversary, or come from programming the random oracle. So we want to use random oracle, but there are many problems with this traditional paradigm. Right, so what can we do to avoid this problem? Okay, so there is something we must do. That's why there is a work here. I mean, there are people studying how to resolve these problems. Okay, there is a different random oracle that one can use in a system. It's kind of, instead of programmable random oracle, it's the observable random oracle model. And in this case, we can still use SHA-256. And the simulator and the extractor will not be allowed to program the random oracle. This will basically resolve some of the problems discussed in the previous slide. And so it will be much better to have basically, for security issues, there will be less points of failure to have a construction that is secure, only having a use of an observable random oracle. So the power of the simulator here, or of the extractor, will be that it can see all the queries done, but will not program the answer, okay? But can see all the queries done by players. Good, it's a weaker assumption. It helps for protocol composability. Unfortunately, it is still impossible to have non-interactive zero-knowledge proofs just with this relaxed version of the random oracle. There are some works that combine the two assumptions in the sense that they use a non-programmable random oracle and then also a common reference string in order to get efficient non-interactive zero-knowledge. Okay? Compared to the simple use of a reference string, these constructions are much more efficient. Okay? They take a benefit from the non-programmable random oracle for efficiency issues. Okay, so the CRS I mentioned it originally. It's a point of failure, significant. We want to get rid of it. So what can we do to avoid the CRS and remaining with the observable random oracle, which is good. It doesn't harm much the security of the system. In case SHA-256 it's used to instantiate it. So there is an idea of paths that can help to avoid the CRS. The idea is to relax the security definition. It is still a point of failure, right? But a different one. Then you choose the one that you like the most. It's basically to run a simulator that can actually go beyond polynomial time and run in quasi-polynomial time. Quasi-polynomial time means that slightly more than polynomial, let's say n to the log n, okay? Instead of 2 to the n, okay? It makes completely no sense to have a simulator running in time 2 to the n, because the simulator running in time to the n is going to compute the witness, brute forcing somehow, and this basically will not give any flavor of the protection of the witness, because so everything can be computed running in exponential time. But if you consider, for instance, some concrete problems, like the discrete logarithm problem, currently, if you run in time n to the log n, you are not going to solve it. You need much more, right? So it makes sense to have, if there is a flavor of security, if you have a simulation with a slightly super polynomial time. Okay, still bad news in the sense that just assuming super polynomial time simulation, quasi-polynomial time simulation, just with this assumption, you cannot achieve NISQ. Okay? There are still impossibility results. All right, we don't give up, and that's so basically in our work. In our work, we try to combine the two assumptions that alone are insufficient to get NISQ. So observable random oracle alone is insufficient. Quasi-polynomial time simulation alone is insufficient. So we combine them, we assume both things, and having together both things, we show in this work that you can have not only a NISQ, you can have a very efficient NISQ. So it's practical, you can use it in practice. Okay, so what are the basic ideas here? I will show you later the construction, but what is the point of combining these two assumptions? Why it is possible that this works? Well, the random oracle still behaves like a random function, and this is beneficial. Doesn't harm much security because you are not programming it. There are no rewinds in what we construct. There is only black box use of the code. Actually, we don't use at all the code of the adversary, so good. There is no non-black box use. That is good. There are no trusted parameters. And for several interesting languages, you can get very efficient proofs. Okay, this is basically what we get combining these two assumptions, what we show you can get. All right, so how do we design a non-interactive zero-knowledge proof system using these two points of failure, because they are, both of them, points of failure, okay? So here, I don't call them just setup, just to make it nice and mild. Then it's only about picking the points of failure that for you are less dangerous. All right, so we start with a building block that is non-interactive witness indistinguishable proofs in the observable random oracle model. It's a notion introduced by Fage and Shamir, and Fage, Lapitot, and Shamir, where basically there is no simulator here. You have basically a prover that might use a witness W0 or might use a witness W1. There are two possible witnesses in this example. And basically the adversary observing the two proofs, will have no idea about which, observing a proof, one of them, will have no idea about which witness has been used out of W1 and W0. This is a tool that is much easier to construct. Indeed, they even exist without any setup. There is no impossibility result. Just with one round NIWI, you need additional assumptions, like for instance, Groton, Strauss, and Sahai constructed this tool using bilinear maps. And okay, so you can see assumptions as another point of failure, right? So we would like not to introduce also more points of failure. So we don't just take their construction, we take a different path. And remember, we also want the proof of knowledge property, the NIWI in the plain model without any assumption of Gauss is not a proof of knowledge. So it's really insufficient for us. So we must follow another path. It's not just an efficiency measure. Okay, there is an interesting result of Fischlin. It showed that you can have non-interactive zero knowledge in the programmable random oracle model, where the simulator programs random oracle, but the proof of knowledge property is proven only observing the queries. That's a good property because we like this, right? And the second is that the extraction is online, there is no rewind. Beautiful. This is part of what we want in our construction. So that's a good starting point, this result of Fischlin. The problem of this result of Fischlin is that for the zero knowledge property, you must program the random oracle. But now you can guess we are going to use quasi-polynomial time simulation. So we might actually circumvent this problem using quasi-polynomial time simulation. Okay, is it really efficient? Yes, it's an efficient transformation that starts from a sigma protocol. What is a sigma protocol? It's a relaxed notion of interactive zero-knowledge proof, relaxed because it enjoys a partial zero-knowledge property, which is honest verifier. It has this format, basically there are 3 rounds. And the beauty of these protocols, the positive point of starting from a sigma protocol is that they exist for many practical, interesting languages. They exist and are efficient, okay, such proof system with 3 rounds. And so Fischlin is able to upgrade this construction in a non-interactive zero-knowledge proofs with those properties. Okay, programmable random oracle in the case of Fischlin. Okay, that's what Fischlin does, and it's extremely interesting for us. Okay, there are some requirements. It's not any sigma protocol. There are some additional requirements. I will mention this later. All right. What is our first result? Our first result is that for now, we don't need zero knowledge. We first construct a building block that is NIWI. But we take Fischlin construction. And actually, we prove that if you start from 2 sigma protocols that are this additional requirement, essentially the additional requirement is that the third message of the sigma protocol is kind of deterministic once the first 2 messages have been played. Okay? This is already a restriction in Fischlin's construction. If you start from basically these 2 sigma protocols, we prove that you can make an OR composition of them. It's a technique by CDS 94, Kramer, Damgard, and Schoenmakers. So basically, you can prove that either one theorem is true or another theorem is true, still with the sigma protocol. And we proved that applying the Fischlin transform, here there is another footnote, a variation actually of Fisherman transform, we have a proof that the resulting construction is a non-interactive witness indistinguishable proof that is in the observable random oracle model, and there is no rewinding, okay, in the extraction. It's a proof of knowledge. So this is good, just it's not zero knowledge. And basically this first contribution that we have is that we have to use a result that is appearing in Asia crypt by Conde and Shelat, because actually they observe that Fischlin's transform does not work on the output of CDS94. CDS94 basically combines two sigma protocol, gets another sigma protocol, but this new sigma protocol, the resulting sigma protocol, is not anymore in the class of sigma protocols that you can give in input to Fishlin transform. Okay. Fortunately, there is a variation of this transform by Conde and Shelat that allows to recycle the same results of Fishlin even for such protocols. Okay. So we follow this path, this variation, and we give a proof that the result will be non-interactive WI. This work, does not, by Conde and Shelat, is about other applications. Finally, they don't want to construct any needs code we do in this work. Perfect. All right. So this proof that we will get now with this approach, we prove that is non-interactive WI. It's an IWI, proof of knowledge, with nice properties in terms of extraction. All right, we want now to upgrade this to zero knowledge, right? So how do we do it? We have a second building block that is a cryptographic puzzle. It's a sequence of algorithms where you generate a puzzle with an hardness factor, and to solve it, you need basically quasi-polynomial time. You can verify a solution efficiently. And basically, it's extremely unlikely that you can solve the puzzle in polynomial time. And moreover, the final property is also extremely important. You can pick an instance of the puzzle also from a sufficiently long random string. So you don't need to run sample. If you have, for some reason, a long random string, from it, you can pick an instance of the puzzle. All right, why is this useful? Because this is our construction. So we start basically with the sigma protocol for proving that X is in L. It's SL, the sigma protocol. Then there is the sigma protocol to prove that I have a solution of the puzzle. There exists also a sigma protocol for instantiation of these cryptographic puzzle systems. So we combine them with CDS94 so that you prove either I know X in L or I have a solution of the puzzle. We combine them with this technique. Then our previous result that I mentioned, with our theorem, we know that applying the transform, the variation of Fishin, you get an IWI. But these together is actually an ITSC. Now, why? Because the simulator, running in polynomial time, will be able to solve the puzzle. And the remaining problem, what is the remaining problem is, where do we get this puzzle in the system? Right? There's no CRS. Okay. Second step, the puzzle comes from the non-programmable random oracle. You give the instance as input to the non-programmable random oracle, it gives you an output a random string, nobody's programming it, good. This random string, we can extract an instance of the puzzle system, cryptographic puzzle, from a random string, so we have it, and we can give an input to the prover and the verifier. So the prover will use a witness for XNL, no problem, basically we'll ignore the puzzle. The verifier will verify the proof using the verification of the variation of Fishin transform. And the simulator will actually have a more sophisticated algorithm, will solve the puzzle, taking quasi-polynomial time. And then we'll use the prover of the NIWI, because it has a witness. Sol is a legitimate witness to run the prover. All right, so we'll get, and we show, of course, a security proof showing that the output of the simulator is indistinguishable from the output of the prover. I can finally conclude my talk. So we basically show that we can have an efficient non-interactive zero-knowledge proof with interesting properties in the sense that it just relies on observable random oracle. It has another point of failure that is the sub-quasi-polynomial time simulation notion that is not as beautiful as the classical one. And it works for a large class of Sigma protocol, still not all, but a large class. Yeah, so it looks many features, many nice features, except these two limitations, but all constructions must have limitations, potential points of failure. And then there is, what is interesting is that is to compare, because this is a jungle, basically. You can have so many points of failure in order to construct the needs, use some of them, and it would be nice to understand which selection is better in the application, and what is, in particular, what is used in practice. My feeling is that in practice, everyone uses whatever is super efficient and not broken yet. And so basically you can have the weird and crazy models and assumptions, but if they are not broken yet, people will use them because there is so much pressure in showing that you have the most efficient cryptocurrency that can scale and so on and so on. So, but it's, I think, extremely interesting to actually start preferring solutions that can really look safer, even though they take 2, 3, 4 times more. Just they are still sufficiently practical somehow. So thank you very much for your attention. This concludes my talk.
Thank you very much, Ivan. Thank you very much for the nice presentation. I would like to open the floor for the questions from the audience. Yeah.
Thanks for a beautiful idea and very nice talk.
Thank you. Thank you. This is recorded, right?
This comment was taken out of context, right? Now, my question is the following. There is a caveat which you didn't mention, which is a very subtle point in this non-interactive zero-knowledge proofs, and this is whether the statement X or the witness W can depend on the common random string, or they have to be independent of each other. Because in those non-interactive zero-knowledge, you first choose the common random string, or you choose SHA-256, and then maybe there will be statement X which depends on this, but the proof will only be able to show that if you first choose X and then you choose randomly the common random string, then everything works okay. But in reality, the order of things is the opposite. So in your construction, are you bothered by the possibility that X or W will depend on the choice of parameters?
Yeah, thank you for the legitimate question. I mean, the point is valid in the sense that there can be needs proof systems that have another point of failure. They are based basically on this weakness that the statement is decided before looking at the trusted parameters. And your work in 1990 showed how to circumvent this barrier, right? No, in our case, we are not affected by this problem because actually there is no common reference string. We use basically the random oracle to generate the puzzle, and it's a random answer. So basically, if at some point, if you see several answers from the random oracle, so because of theorems x1, x2, x3, they will not help you to generate a new theorem. Why? To prove a malicious proof, because then you will have to give it an input to the random oracle again, and by definition, it's a new query for the random oracle, new random string, uncorrelated to everything else you saw. The fact that it's uncorrelated to everything else you saw so far, allows us also to prove security against this adversarial behavior. Thank you very much for the question.
Yeah. Question back.
Thank you very much for a great presentation. So at the beginning, you motivated the talk by Zcash. So of course, they use Zcash logs that we have succinct proofs. So my question was that, do you think we can go to the succinct proofs with these techniques?
Okay, for Zcash, there are various points of failure in what they do. Okay, I mentioned this issue, right? Whatever you pick, you should worry. So there is, first of all, there is a knowledge assumption that to prove extraction. That is also problematic in case of concurrent composition. You don't have a universal composability with such assumptions, for instance. Then also they have number theoretic assumptions, also specific ones. They get succinctness, which is beautiful. We don't get such succinctness, but wait, it all depends on what you are proving, because when you prove something about a large statement, you need succinctness. But if I'm just proving, I know the secret key of a given public key, who cares about succinctness? Having a linear proof is fine. And they have a super slow prover in snarks, while here the prover is super efficient. Okay. So I don't know if I answered your question. What was the final part, maybe?
Yeah, I mean...
I just made a comparison, but...
Yeah, of course, that's true that if the language is simple, so we don't need this succinctness, but in case of ZK, let's say, cryptocurrencies like as...
That is fundamental. Yeah, you cannot use this system replacing...
Exactly.
That's what... I fully agree. In that application, you have a gigantic statement. You need succinctness, okay? This is very good for many applications, but not that one.
True.
Perfect.
Okay.
Good
so,
point.
and you mentioned that we have to pay on something. So I guess you pay on this polynomial quasi.
Right. That is a relaxed security notion, right? Yeah. And you pay on the fact still you believe on the observable random oracle. SHA-256 can fail as an observable random oracle, of course. So these are the two potential points of failure. Yeah.
Okay. Thank you very much.
Thank you very much.
Thank you very much. Any other question? Oh, okay, I have a question. Me.
Okay, yeah. So, sorry, because of the light, I couldn't see you, yeah.
That's fine. You mentioned something about formal verification for the zero trust or formal modeling.
I mean, the point is, no, it was mainly because when I defined the properties of a zero-knowledge proof, I gave kind of informal properties, completeness and zero knowledge. I mean, one can have really the formal properties, but of course they are in the paper. For the talk, I saved you from this mess, right, going into the details of the formal properties of what is a non-interactive zero-knowledge proof. Just that, but yeah.
So you basically have some knowledge about the formal verification for security protocols, and do you think this security protocol?
I mean, it is formally it's formalized what is the verification procedure and why it works.
Which tool maybe you advise maybe to use verification for the zero knowledge on this one?
Okay. Whenever you design a non-interactive zero-knowledge proof system, okay, it's part of the system that you design, and we did it. You have to show what are the steps that a verifier should do to verify proof. And when you show this, I mean, we show them in a pseudo code, but then you can implement in any language you want. Okay, so this is an interesting point because, I mean, you can have, of course, a paper where you prove that everything is secure and so on, but maybe because there is a proof, but maybe there is a bug in the proof and nobody sees it. So your point is that can you have a different way to verify such proofs and so on? I mean, there is a community doing that, but it's orthogonal to what I did in my work. So.
Thank you very much.
Thank
you.
Thank
you very much for Ivan. Please.
Thank you.
We will go now for a short break for 20 minutes. Yeah, and in 11:15 we will start again. Thank you very much.